Hi, in this video, we study maximum likelihood estimator. So we have studied that the multiple linear regression is estimated by least square, but this least square estimate for parameter beta is a special case of maximum likelihood estimator if epsilon j's are IID normal. So we review a notion of maximum likelihood estimator. So this is a basic example and not related to maximum likelihood. The multiple linear regression. So consider the situation that we randomly pick up a die out of 3 unfair dice, X, Y, and Z. And we roll it once. Then suppose that you don't know which die that you chose, but you can observe the result. So suppose the result is the 2, the face of 2. Then, okay, so we have the 3 dice, X, Y, and Z. X is actually a fair die, so 1/6 probability for all 6 faces. And Y is a loaded die, and it will have the face of 1 with probability 1/2, and the 1/10 for other cases. And Z is more complicated. 1 probability is 30%, and 2 with 1/2, and the other case 1/20. And if we observe the outcome is 2, then we compare these 3 cases. And actually, without any condition, we have 1/3 chance each to pick X, Y, or Z. So if the outcome is 2, then since the Z has higher probability to have 2, actually the probability that we have picked up Z increases. So we decide the most likely choice of our die is the Z. So that is the so-called maximum likelihood estimator. So the maximum likelihood estimate is Z in this case. And this function, so X to 1/6 and Y to 1/10 and Z to 1/2. So this function is called the likelihood function. And basically, the maximum likelihood estimator is the maximizer of this function. So 1/2 is largest. So this is a kind of special concept in terms of probability, because the X, Y, and Z, so these die, each of these dice determines the probability space. So total is 1, total probability is 1. So if we see this table just horizontally, that is just the usual way to do probability theory. But the maximum likelihood estimation, think about the function, this table vertically, and think about the function from this possible model to the values. So this is the concept of the maximum likelihood function and the maximum likelihood estimation. And in reality, we don't decide between rare situation, but maybe the first possible choice is that some variable follows the normal 0.5 and variance 1, and the second case, the variable follows the normal, the 1, 1, and third case, the variable follows normal 1.51, and we consider which model is most likely. So we choose between these 3 models. So that is a typical case for maximum likelihood estimation. Okay, so think about the linear model now, and what is the MLE? Yeah. So at first, we think about a little bit simpler case. So since linear regression, we only have the one random part, epsilon. So epsilon follows the normal, the 0 sigma square. So we think about the probability density function, the PDF of this epsilon j. And since this is the normal random variable, so this has the density of this, the 1 over sigma times square root of 2 times expectation of the epsilon j square over 2 sigma square. So if we have n terms, then that is the product j is equal to 1 to n of this function. And usually the taking logarithm makes it easier to think likelihood function because the product becomes a summation. And summation is easier to deal with usually because, for example, that we can apply the central limit theorem. And if we take the logarithm, then this function becomes this, the 1/2 times the log of 2 pi. This is anyway constant minus the log of sigma minus the epsilon j square over 2 sigma square. And the linear model is x is equal to the x beta, y is equal to x beta plus epsilon. But anyway, so we will minimize, we want to minimize this error size, to be exact, that we want to minimize the sum of epsilon j square. So that is the, the criterion to estimate beta. So so this likelihood function can be also used for this the multinomial linear regression. So okay, so least square estimate is minimizing this summation of epsilon j square, and the maximal likelihood estimate is maximizing this quantity, the number 4. So we will show that these two criteria are actually the same. Okay, so the previous figure, the expression of the log likelihood function is here. So we want to minimize, we want to maximize this with respect to sigma first. Okay, so actually the sigma is a kind of the nuisance parameter. So we have basically want to estimate beta, but we have another parameter sigma. Epsilon follows normal sigma square. So basically we are going to estimate this with respect to the sigma and the beta at the same time. So at first we maximize this with respect to sigma and to remove sigma. Then after that we determine beta. So we take that strategy. So we differentiate this, the quantity number 4 by sigma. Then log of sigma, negative log of sigma becomes the negative n over sigma. And the last term, the epsilon j square over 2 sigma square. So that becomes summation of epsilon j square, summation here, and divided by the sigma cube, because the 2 becomes, so the sigma square, so we differentiate to sigma square, so 2 appears and they cancel with the denominator 2. The negative also cancels. So finally, we get that the sigma square should be, so estimate for sigma square should be the 1 over n to the 1 over n times the summation of epsilon j square. So that is just the we solved this equation. Yeah. So we plug in this number to the original, the log likelihood function number 4. Then that becomes this function. So it's much simpler. Why? Because the sigma square is estimated by summation of epsilon j square, and that term cancels. So it basically becomes constant. So only one sigma remains. And the sigma, we plug in the sigma square is equal to the summation of the epsilon j square. So actually the quantity number 4, equation number 4 becomes this equation number 5. So the maximum likelihood estimator minimize this quantity. They maximize this quantity. So, but this is negative, the log of this function. So basically, we have to minimize this quantity. Since n is already given, so just the sample size, so that means that we minimize the sum of epsilon j square. So that means the minimizing the sum of squares, the error term squared, the square of errors is equivalent to maximizing the likelihood function. So that means that if epsilon j follows normal distribution with the mean zero, the variance sigma square, then that is equivalent to the least square estimator. Yeah, so we introduced the concept of maximum likelihood estimator and showed that the MLE and the least square estimator are equivalent if the so if the epsilon that follows the normal distribution with variance, the fixed variance sigma square.